Okay, kids, continuing on with limits and still largely evaluating them from the graph, but we're going to start to make that connection between algebra and the equation and the graph that it produces. So hopefully this brings back some properties you remember and you're not solely relying on the graph. But this first graph here, if you'll notice, is the graph of this function g of x, and you might even remember what's making certain things with it having a vertical asymptote, a horizontal asymptote, a hole. That's just a regular old point that I've highlighted there. But just for fun, if you want to think about what made some of these properties, is this rational function would factor to this, and then there was a common factor which could be canceled. Now there were two x values where this function did not exist. Those are the two x values that makes the denominator 0, and that would be at -3 and +2. But you'll notice that the quantity that gives you +2 actually cancels away. So that's what they call a removable discontinuity in the graph, and the x plus 3 is a non-removable quantity. So you'll notice that at -3, the x value here, which is still stuck in the denominator, that's what causes a vertical asymptote. At +2, the graph does not exist, this function does not exist, but since it cancels, that's what yields a hole at +2. And the way you get the y-coordinate of the hole is if you were to plug that value of 2 into the reduced function, now that you've canceled away the part that will make it, undefined. So if you plugged 2 in, you would get 4/5, 4/5. So that's the y-coordinate of the hole. And you'll also know it has a horizontal asymptote at y equals 1. Hopefully that's easy, because then you're looking at the numerator compared to denominator. They have the same degree, and so you look at the ratio of their coefficients when that's the case. And 1/1 is, of course, 1. So don't need to know all that stuff yet, but it helps if it's still in there, and you can kind of dig it up as we go along. So anyway, evaluating these limits from the graph, the limit of this function as x approaches -3. So -3 is right here, and as we approach -3, we are approaching a vertical asymptote, which means we are going to infinity or -infinity, but either way, that is not leveling off at a number, so we say DNE unbounded. DNE unbounded behavior. The limit of the function as x approaches 2. So as x approaches 2, 2 is right here. As we approach 2 from the left and the right, the y values are both approaching the y value of that hole, which is 4/5, which is why it's going to be important to remember how to get that y-coordinate of the hole. Plug into the reduced function, because that's all you're finding. The limit of this function as x approaches 5. 5, there's actually nothing too interesting happening at 5. It's just a normal point. The y value is 7/8, and that's what the y values are approaching. That you could get easily from the equation just by plugging 5 in, right? 5 plus 2 is 7, 5 plus 3 is 8, 7/8. And the limit of this function as x approaches infinity. So that is going to the right, and as we go to the right, then we're saying, what is this function approaching? It is approaching that horizontal asymptote value of 1. So that's easy, done, but a little brush up on what we were doing the day before. Now looking at this function, this is kind of an interesting function, that it's the absolute value of x plus 3 over x plus 3. So if you'll notice that, and it's got a negative out in front, that regardless of what x value you plug in, you're going to get a very similar response. For example, if you plug in 1 for x, you'll get 4, and the absolute value of 4 is 4/4, and 4/4 is 1, and you get -1. So any x value you plug in here, you're going to get -1 from. At -3, the graph is undefined, because you would get 0 on the denominator, and so notice you kind of have this strange situation. It's not exactly a hole, because I can't quite cancel it because of that absolute value, but it's not a vertical asymptote either, because we're not going to infinity or negative infinity as we approach that spot. If you plug in anything infinitely close to -3, if you plug in -4, for example, -4 plus 3 is -1. Absolute value of -1 is 1 over -4 plus 3 is -1, and then this negative out in front makes it all be +1. And that would be the same regardless of what x value you plug in, as long as it's to the left of -3. -3.0001, plug that in, you're going to get +1. Anything to the right of -3, -2.9999999, you're just going to get -1 from. If you plug in 1,000, you're still going to get -1. So it's kind of an interesting little quirky function. But in terms of answering these limit questions, as x approaches -3, so as we approach -3, from the left, the function is approaching 1. It actually is 1. It's not just approaching it. And as we approach -3 from the right, the y value is approaching, or is, -1. But either way, they're not going to the same value. So that is where we'd say the limit does not exist. And that is because the left does not equal the right. They're going to two different values. The limit as x approaches 0, here's x equals 0, and as we approach 0 from the left and the right, we're just sitting here on the curve, nothing big, we get -1. As x approaches -infinity, so that's going to the left of this function, that function is staying right at +1. So it's not just approaching 1, it is 1, but it's not changing. And as we go to the right, as x goes to infinity, what are we getting out? We're getting -1 for y, for this value of h of x. So that's it. Okay. Now on the back side here, we are talking about two piecewise function examples, and I'm expecting you to sketch your own graph to answer the limits. In the future, and maybe even now you're getting there, you might not even need the graph if you really know what's happening, but let's just take a look to cement that visualization. Remember, a piecewise function has two or more pieces, but you only use those equations for certain x values. So this is saying you're graphing x plus 3, but only for x values that are less than or equal to 1. So you could make a table if you want, and only use x values that are less than or equal to 1, 1, 0, -1, and plug into here, and you'll get 4, 0 plus 3 is 3, -1 plus 3 is 2. And you plot this point because it's equal to, you plot that with a closed point. Or you might just say, look, I could have just graphed this. It's a line with a y-intercept of 3 and a slope of 1. So starting at 3, up 1 to the right one, down 1 to the left one. But just remember, you're only graphing this function up to and including that point at 1, 4. That's sort of the end of that portion of the graph. And then you're picking up this function, which is another line, but only for x values greater than 1. Now remember, that doesn't mean you should start with an x value of 2. I know that's greater than 1, but what about 1.01? What about 1.001? 1.00001? So whether you're graphing or making a table to get you started, you're still going to plug in that 0.1 to get a sense of, well, the value here that you're starting with, which will be 2. But to show that it's not included, we plot that point with an open circle. And then plugging values bigger than 1. Plugging 2 in, you'll get 0. Plugging 3 in, you'll get -6 plus 4. You'll get -2. And so you could have, again, just used your knowledge of y equals mx plus b to start here. It's a y-intercept of 4 and a slope of -2. So down 2 to the right one. And keeping in mind, well, that's where we're going to start the graph, because that's the x value of 1, where we start this portion of the function. So we start there, but again, we use an open circle to show we're not including that point, but right up to it. And then 2, 0, down 2 to the right one, down 2 to the right one, or using the, points from your table, you've got that. And so the important thing with a piecewise, at least in terms of limits and calculus, is that at this x value of 1, which is kind of what I call a borderline value, where it changes from this equation to this equation, notice there's a discontinuity in the graph. There's a break at 1. It's what's called a jump discontinuity because it just jumps down to there. The pieces aren't connected. So keep that in mind when you're doing your limits. This limit, what is the limit of this function as x approaches 3? So that means, remember, you're zeroing in on when x is 3. So I'm really just thinking about that neighborhood. And as you approach that point from the left and the right, the y values are approaching -2. So that's the answer to the limit, -2. What about as x approaches 0? As x approaches 0 from the left and the right? Well, here's x equals 0. I'm looking at that spot on the graph, and as I approach that from the left and the right, I know there's like a discontinuity and all kinds of stuff, but as you get infinitely close to 3, to x equals 0, the y values are approaching 3. So that limit exists, and it's 3. What is the f of 1? That's not a limit. That's not calculus. That's just saying what is the y value when x is 1, and that would be 4. Hey, if you've got a point, you've got a y value. And what is the limit of this function as x approaches 1? And now here we go. This is the important thing. As you approach 1 from the left, you're approaching a y value of 4. And as you approach 1 from the right, you're approaching a y value of 2. 4 from the left, 2 from the right. That's not the same value. We would say the limit does not exist. Left does not equal right. And so again, that's just to illustrate the difference here between, it's not just saying what is the y value at 1. It's really talking about from the left and the right. So in the future, where we're headed with this is that when we ask for a limit at one of these borderline values, so when you see this piecewise, 1 should stand out as, hey, this is a special x value. And if they ask me for the limit as x approaches that value, there's a good chance that the left and the right won't be going to the same y value. So you'd have to substitute 1 into this and this one. And if you plug them in algebraically, you'll get 4 and 2, the same values that we got graphically. And so limit does not exist at that one single x value. Okay, so we see this one here. The key x value to watch out for, the borderline x value, is the -1, where it changes from this to this. But let's graph and visualize. This is a line with a y-intercept of -2 and a slope of -3. So if you want, let's try to graph this. But remember, we're only graphing it for x values to the left of -1. So y-intercept of -2, slope of -3, that would be up 3 and to the left 1. That would be the first point, but with an open circle. And then up 3 to the left 1, up 3 to the left 1. This is a parabola with a vertex at 0, 0, opening upwards. But if you want to know where those other x values are, if you're a little shaky with your parabola graphing, you might want to plug in values. When you plug in -1, which is the sort of start of this portion of the graph, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So you get this. And what you actually get is, since this point is a closed circle, because we're including -1, it actually fills this hole from that other graph, which just means that the pieces are connected. We have a line on this side, and it's connected perfectly to this parabola. There's no break, there's no discontinuity. And so now we can answer these limit questions. What's the limit as x approaches -2? As x approaches -2, we're talking about right there. The limit is 4. as x approaches 0, that's right here, the y value is 0 from the left and the right. The f of negative 1, that's 1. And what's the limit as x approaches negative 1? Well, since those pieces were connected, they're both approaching that y value of 1 from the left and the right. So this is just an example of how the limit can exist at one of those borderline x values on a piecewise function. It's if they're going to the same y value. And you could test that algebraically. If that's the only value you really cared about and didn't want to draw the whole graph, you could test that algebraically by simply plugging negative 1 into each piece. You know, when you plug in negative 1 to this piece, you're testing the limit from the left, and you would get 3 minus 2 is 1. Plug negative 1 into here, negative 1 squared is 1. They're both going to positive 1. They agree, then your limit exists, and that 1 is your answer. Okay, hopefully this is taking your limit knowledge a little bit further. We're getting a little more comfortable with the notation and visualizing what's happening, because we're definitely going to take it up a notch in the next couple days. So any questions, just ask away. Have a good day.